How would you measure this without satellites or computers or even a telescope? 2,300 years ago, an ancient Greek astronomer came up with an ingenious and sort of simple way to do it with triangles. Aristarchus of Samos found a 4-step mathematical process to calculate the relative sizes and distances of the sun, moon, and earth using just a few simple measurements. His steps worked so well that following them today with modern data gives us stunningly accurate results. But this math convinced him that the earth revolves around the sun instead of the other way around. The available evidence suggested that his theory had a fatal flaw, and it was soon rejected for close to 1,700 years. It wasn't until even later, in the age of the modern telescope, when data showed that Aristarchus was right. Here's how it works.
So the first step in the process is to see the sun and the half moon in the day sky. And his brilliant idea is what that actually means. What does it mean that you have half a moon? Pretend this is the moon. Sure. The sun is shining on it, so it's always lighting up exactly half. There's half that's being lit up and half that isn't. But as that moon moves around the earth, what we'll see if the moon is here relative to the sun, what we'll see is just a little sliver of the moon being lit up. So when we see exactly half of the moon being lit up, it's because there's a right angle at the moon in this triangle, in the earth, sun, moon triangle. But we're on the earth, right, which means we can measure the angle between the sun and the moon at the earth.
The ancient Greeks understood very well that the sides of any two triangles with the same angle measures also have the same proportions. No matter how big or small these triangles are, we can say that they are similar. So if you just know the angles, then you can calculate the relationship between the side lengths, even if it's for a triangle bigger than all of planet Earth. He would have looked up into the sky and seen the moon there and the sun there and said, you know, with arms or whatever, like, this is the angle that's formed. And then we try to put some numbers to it, which is hard.
Yep.
In this book, Aristarchus says that the angle formed by the sun and the moon is 87 degrees. He calls it a quadrant minus a 30th of a quadrant, where a quadrant is 90 degrees. Now, this number, it's wrong. It's going to underestimate the distances. We'll see later how changing this angle by just a little bit changes the final result by a huge amount. But Aristarchus might have known that he was underestimating things, and he might have been okay with that.
Qualitatively, the fact that we have a half moon there and a sun over there, and at my body, I see a very wide angle, already has very important qualitative information, not yet quantitative.
Yes.
But if we try to imagine a right triangle where the other angle is very large, well, that means that that other point is very, very far away, especially relative to the distance between this side.
As we'll see, Aristarchus's underestimated value was still large enough to lead him to a powerful argument for why the Earth must revolve around the sun. But this technique of measuring right triangles and calculating the relationships between their sides, of taking that which you cannot touch and turning it into something that you can, it's at the core of what would soon become known as trigonometry, an indispensable tool for scientific progress over the millennia. Now, this was a time before ratios of right triangles like these had been cataloged into extensive trigonometric tables, so Aristarchus used complicated geometrical arguments to get a range of values for his answer. But given a big enough space and some nice, clear measurement markings, we can accomplish something similar by building a scale model. I'm going to use this for the Earth, this marble for the moon, about 12 feet away from the Earth. This is going to be our sun. We've got an angle measurer. Okay, so let's make this 87-degree right triangle.
We couldn't have had this idea in the summer.
I know, right? A measurement of 87 degrees predicts that the sun is about 20 times further away from us than the moon. So that gives Aristarchus an idea of the relative distances involved. But how do we use this information to figure out how big everything is? Well, luckily, there's a time when we see the sun and moon in exactly the same part of the sky, during a solar eclipse.
This is the plane of the ecliptic. So this is how the Earth moves around the sun. And the plane of the moon almost moves in the same plane.
But its orbit is actually 5 degrees off from the plane of the ecliptic.
And so most of the time, the moon will either pass above or below the sun, but very rarely, it will pass directly in front of the sun. And when it does, you get that total eclipse.
If we draw triangles to represent our line of sight to the sun and the moon, then the fact that the moon perfectly covers the sun during a total solar eclipse means that these two triangles are perfectly proportional. The ratio of the size and distance of the sun is the same as the ratio of the size and distance of the moon. This is a remarkable cosmic coincidence, and this fact about the relationship between the sun and the Earth's moon makes the rest of these calculations possible, because it means that when Aristarchus claimed that the sun was 20 times further away from Earth than the moon, he could also say that the sun is 20 times bigger than the moon. And even though we know that that number is too small, it was the largest estimate for the size of the sun that anybody had ever seriously proposed at the time. Before Aristarchus, the great mathematician Eudoxus thought the sun was 9 times bigger than the moon, and there was another astronomer named Phidias who said it was 12 times bigger. Now, we barely know anything else about this guy Phidias, but he's actually kind of a key figure in the story, because Phidias had a son, and that son grew up to be the greatest mathematician of the ancient world, Archimedes of Syracuse. And the reason that we know anything about Aristarchus saying that the Earth revolves around the sun is because Archimedes told us about it. Aristarchus's original book on the topic has been lost forever. Not only does Archimedes tell us about Aristarchus's heliocentric theory, but he gives us some practical tips for how to carry out an experiment to verify some of the measurements that Aristarchus used to calculate these sizes and distances. Because the next step in solving this problem is figuring out how many moon lengths away from Earth the moon is, and how many sun lengths away from Earth the sun is. To do this, Archimedes describes an experiment that he says he did himself to confirm the measurement of the sun that Aristarchus used for his next calculation. And he does it by creating his own mini solar eclipse. Remember that triangle we said was formed by our line of sight to the sun or the moon? Well, if we make another similar triangle, but this time we use an object with a known size, then we can calculate the actual ratio of the size of that object to the distance from our eye, and we can know that it's the same ratio for the triangle formed by the sun. Once again, we're measuring that which you cannot touch by turning it into something that you can. Now, Archimedes' experiment involves looking directly at the sun.
He did it at sunrise with the sun.
Yes, you should not do that. Please don't do this at home.
Don't do this with the sun.
Instead, you can wait for a full moon.
Take a dime and you tape it to the window, and you walk away from the window until the dime perfectly covers up the whole moon that you can see in the sky. It's like a dimal eclipse or something. And the question is, how far away are you standing from the dime when you do that? And the answer is like 90 inches. So the ratio of 0.7 inches, which is the diameter of the dime, to 90 inches, which is the distance, is 1 in 125. It's the angle subtended by the moon, which is a half a degree. And so you learn the ratio for the moon and simultaneously for the sun.
At this point, Aristarchus had calculated that the moon is about 125 moon lengths from Earth, and the sun is about 125 sun lengths from Earth. And he also said that the sun is 20 times bigger than the moon. But we still need a way to measure all of this stuff in terms of the size of the Earth. And for that, we have to wait for a lunar eclipse. About twice a year, the Earth comes perfectly in between the moon and the sun, casting a shadow on the moon as it blocks the sun's light. While the light can move in a straight line around any part of the Earth's surface, there's a cone-shaped shadow in the middle called an umbra, where the sun's light doesn't reach. And when the moon enters this umbra, we see a lunar eclipse. But the distance across the circular cross-section of this cone-shaped umbra is bigger than the moon itself.
So you time how long it takes for the moon to go from entering totality to being in totality, and let's call that 1 hour. Okay, so that's like the top of the moon traveling the diameter of the moon. And then we're going to time when the moon first begins to enter totality, when it first starts getting closed off, until it first starts exiting totality. So that's when the top of the moon has traversed the entire umbra, and we'll call that 3 hours.
So we're using the time it takes the top of the moon to travel 1 moon length as a measuring stick for the umbra. If it takes it 3 times as long to cross the umbra, then that means that the umbra is 3 times the size of the moon. Now, if you go out and time this yourself at the next lunar eclipse, you're going to get a value that's smaller than 3. But we're assuming that we're seeing the longest possible lunar eclipse, one where the moon goes through the largest part of the umbra. And we're also rounding up to account for other complications, like the fact that the moon travels in an arc. Now, timing the length of eclipses with things like sand timers was an obsession that went back to the Babylonians. And while he might have had other measurements available to him, Aristarchus, again, slightly underestimated things when he used a value of 2 here. From there, he once again set up a pair of similar triangles to find the relationships between the size of the Earth and the sizes and distances of the sun and the moon.
So we have the sun, the Earth, and the umbra, and we're going to draw parallel lines to this center line. So this pair of triangles is a similar pair of triangles. And this length is from the radius of the Earth minus the radius of the umbra. This distance is the distance to the moon. The umbra is where the moon is. That's the distance to the moon. On the other side, we have this height, which is the radius of the sun, minus the radius of the Earth. And what is this horizontal? It's the distance to the sun. And so those two must be in proportion. Those two ratios are the same.
Since Aristarchus says that the sun is 20 times further away from us than the moon, we know that every dimension of the triangle on the right is 20 times bigger than the corresponding part of the triangle on the left. So we could say that the radius of the sun minus the radius of the Earth is equal to 20 times the radius of the Earth minus the radius of the umbra.
Well, the radius of the sun, we're saying, is 20 times the radius of the moon, and the radius of the umbra, we're saying, is 3 times the radius of the moon. So you get this equation, and if you divide both sides by 20, then you have the radius of the Earth minus 3 times the radius of the moon is equal to the radius of the moon minus 1/20th the radius of the Earth. Well, that 1/20th is going to be a rounding error, but the 3 radii of the moon, we move to the other side, and we get 4 radii of the moon is 1 plus 1/20th the radius of the Earth, or roughly just the radius of the Earth. So the Earth is 4 times bigger than the moon, approximately.
With Aristarchus's measurement that the umbra is twice the moon's diameter, he would have found that the Earth was 3 times bigger than the moon instead of 4.
And so based on Aristarchus's calculations, the sun is about 20 times the size of the moon. And that also means it's about 7 times as big as the Earth.
These estimates put the moon at about 42 Earth lengths from us, which is a little above the actual value, and the sun at about 840 Earth lengths away, which we know is a significant underestimate thanks to that 87-degree measurement at the start. But even with these numbers, it's still completely clear that the sun is much bigger than the Earth and very far away. Think about this. How likely would it be for a much bigger object to orbit around a much smaller one? If you tie a golf ball and a basketball together and you kick the basketball, what are the chances that the basketball spins around the golf ball? But if you do the reverse and you kick the golf ball, then of course it would go around the bigger ball. This everyday idea that bigger things affect the motion of smaller things more than the reverse was key to Aristarchus's argument for heliocentrism. But Archimedes also mentions a possible problem with Aristarchus's theory. Because if the Earth is moving relative to the sun and all of the other stars, shouldn't our view of the stars change as we move around in the sky? The Greeks thought of the stars as being like little flecks of paint on a giant celestial sphere. So in this model, moving closer to or further from one part of the sphere would lead to a deformation. Some of the stars should look bigger or smaller in your field of view compared to other stars. And since we don't see that, wouldn't the theory that the Earth moves around the sun imply that the universe is far bigger than anyone had ever imagined? The Greeks didn't have an answer to this question, and maybe partly as a result, Aristarchus's theory that the Earth moves around the sun eventually lost out to the theory that the Earth is the center of the universe as promoted by Ptolemy. This idea of geocentrism was a mathematically sophisticated theory. Even though we know now that its core assumption was wrong, Ptolemy's model successfully predicted the behavior of the heavens, and it became the dominant theory for centuries, reaching the status of religious dogma. But there was one more question that Aristarchus's calculations couldn't quite answer. Because while he'd found estimates of the relationships between the sizes and distances of the Earth, Moon, and Sun, using nothing but pure geometrical thought and some very rough measurements, Aristarchus never guessed the actual sizes of these things. If you tried to measure the distance to the Moon with a ruler, what would you get? Knowing how these values are related means that having just one of the numbers snaps the rest of them into place. And the one that we have the best chance of finding directly is the size of the Earth. But to find that, deductions based on pure thought and estimated measurements alone wouldn't be enough. It was going to take direct, on-the-ground data. And what better place to go for this than Alexandria, Egypt, which had quickly become the new intellectual center of the recently expanded Hellenistic Empire since the military conquests of Alexander the Great. And it was data collected here that led a mathematician a generation younger than Aristarchus to find an answer. The great Eratosthenes. Here's how he did it.
So there's a well in the center of Cyan. This is modern-day Aswad, Egypt. And the only time of the year when you can see to the bottom of the well is at high noon on the summer solstice. And the reason you can see at the bottom of the well is, of course, because the rays of light must be going straight down, so perpendicular to the sphere of the Earth's curvature. They're normal to the Earth right there. But the sun, given that the sun is so far away, we can just assume that all of the light coming from the sun is coming parallel. So he knows that Alexandria is about 500 miles away from Cyan, almost due north from Cyan.
Legend has it that he calculated this from the number of days it took a caravan of camels to walk between the cities in a straight path.
So in Alexandria, there's a big pole, an obelisk, and you can measure the shadow of that pole also at high noon on the summer solstice. And what you measure is an angle which is about 7 degrees. Now 7 degrees is about 1/50th of a circle. And again, by similar triangles, if you were to extend that obelisk which is also normal to the sphere, it's pointing straight out of the sphere, which means if it were to turn around and go straight down, it would go straight to the center of the Earth. The well also, if extended, would go straight down to the center of the Earth. So you get this triangle with two parallel lines, the parallel rays of the sun, and a transversal which passes through the obelisk. And so if there's a 7 degree, if there's a 1/50th of a circle degree at the obelisk, at the tip of the obelisk, that means that there's a 1/50th of a circle degree at the center of the Earth. And so if it's 500 miles from Cyan to Alexandria, well, that's 1/50th of the entire circumference of the Earth, which means the circumference of the Earth is 500 times 50, namely 25,000 miles, which is pretty darn close to the modern measurement.
18 centuries after the time of Aristarchus and Eratosthenes, a Polish astronomer named Nicholas Copernicus studied the ancients, including Aristarchus, and developed his own theory of the cosmos. He also came to the conclusion, contrary to the accepted wisdom of the time, that the Earth is not the center of the universe. He said that it and the other planets orbit around the sun instead of the Earth. Gradually, his theory attracted a critical mass of supporters who were among the most serious scientific thinkers of the time, like Johannes Kepler. But the theory had detractors too. At one point, the idea was so politically and religiously unpopular that some scholars were afraid to engage with it publicly at all. And the Catholic Church sentenced Galileo to house arrest for the last 9 years of his life for promoting heliocentrism. But not everybody who questioned Copernicus's theory did it for religious reasons. There were still evidence-based scientific objections too. In particular, an astronomer named Tycho Brahe pointed out that if the Earth really is moving around the sun, we should see changes in the positions of the stars, deformations in our view of the celestial sphere. It's the same objection as Archimedes' objection to Aristarchus so many years earlier. And the fact that no such stellar parallax had been detected was an unresolved issue for Copernican heliocentrism for many years. Now today, we know why they couldn't see stellar parallax. It's because the universe is far bigger than anybody in ancient Greece or even the 16th century could have possibly imagined. The stars aren't just little dots painted onto some giant celestial sphere. Each one is its own distant sun with its own solar system. And these stars are parts of galaxies, the size and breadth of which is staggering to comprehend. Remember that inaccurate 87-degree measurement from Aristarchus? Well, the real measure of that angle between the sun and the half moon in the day sky is 89.86 degrees. Shifting the angle by less than 3 degrees completely blows up the model.
For these modern measurements, we're going to need to make it a lot smaller, and we're going to need to bring it a lot closer together so that it fits on the football field. So at this scale, the Earth is going to look like this. It's about a little less than half an inch. And that means the moon, which is a quarter the size of the Earth, looks like this. And then we're going to have our sun, which is 400 times the size of the moon, a little more than 100 times the size of the Earth, which looks like this. It's going to have to go pretty far.
With modern measurements, we know today that the moon is on average about 30 Earth lengths away from us, while the sun is roughly 11,500 Earth lengths away. In the scale of our model, where the Earth is less than half an inch in diameter and a foot away from the tiny moon, and the sun is over 3.5 feet across and located well past the other end zone of the football field, the nearest star would be a staggering 21,000 miles away. That's like flying from New York to Hawaii the long way. At these astronomical distances, stellar parallax is impossible to detect without a telescope. So it wasn't until the early 1800s when Giuseppe Calandrelli became the first to document that the star Vega changes its position in the sky ever so slightly over the course of the year. And in the modern era, the way that we calculate the distances to the nearest of these faraway stars is by measuring this parallax and forming triangles to extrapolate their distances. And so today, as it was in the time of Aristarchus, we continue to measure that which you cannot touch using the art of trigonometry.